Thank you, Yonatan. And by the way, thank you for organizing Blackbox NLP with all your co-organizers this year. There's always been so much interesting stuff at this workshop, and I've never had an excuse to come to an NLP conference before, so I've always been really interested. We don't have a Blackbox CV event, and I've been always envious of Blackbox NLP. It's just such a great forum. So thanks for all your work putting this together over the years. It's a real honor to be able to participate in it, and it's been fun to meet people, and I hope to continue to meet folks interested in interpretability through EMNLP this week. Anybody who's interested in chatting with me, you can always just approach me or send me a note on Twitter or email anytime. So my background is, Yonatan noticed that I was a little bit older for a beginning academic, old enough that my son is going through the process at the same time as me. I was a practicing software engineer for my whole career before I was sort of lured back into academic research. And really the lure is all this amazing stuff that has been happening in machine learning over the last decade. And so I want to sort of begin by acknowledging that there's really genuinely been something interesting happening in our field. I think that, we can, standing from inside here, let's see, do I have a clicker? Does think that this clicker works? Clicker, click, 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 click. Oh, maybe. Sorry, I should have tested this clicker ahead of time. Is that out of batteries? Is it working now? Yeah. Oh, it's just a focus problem in Windows or something. Okay, that's great. So, yeah, there's something genuinely interesting. So I really liked Catherine's talk earlier today. She showed all these phase change diagrams where there's a little bump in the training. She said, oh, this is a phase change. And I wanted to reinforce that point. I think these phase changes are real. There was a very interesting poster I saw at NeurIPS last week at a workshop that probably hasn't gotten that much notice, but I wanted to highlight this is work from Lewis Kirsch and several co-authors. But he's taking this physics point of view on how to understand these large models that are trained in different ways. And he really can see these phase changes happening, these phase change diagrams showing up in a way that really, is evocative of phase changes that you see in physics. There are things that are happening here, and it does depend on the model architecture. If you choose a transformer and you push it towards certain classes of problems, then they actually genuinely seem to be learning in a different way than earlier architectures. And so he calls this phenomenon the learn to learn, or the meta learning. This actually came from the meta learning workshop. I heard some negative reactions to calling in-context learning meta learning, but even in the meta learning workshop where they've been studying hyper networks and other things, I think they've adopted a curiosity about these in-context learning problems as well in their community. And they think there's some phase change thing happening there as well. So I think this is really interesting. Deep networks are genuinely surprising. They've surprised us repeatedly over the years, from the very earliest days when Rosenblatt, thought, hey, let's take this deep network model and can we make self-programming computers? He had 64 parameters, and he convinced himself that there were going to be walking, talking, self-conscious machines. But actually, it didn't really take off. It wasn't really useful until quite a bit later when we had networks in the 1980s and 90s. Lynette was quite famous. And then the earthquake that brought me into the field, the thing that really, made me realize, oh, we've got to like switch tracks and study this. And I don't know how many of you were pulled in around the same time, but when machine learning was getting quite mature in the last few decades, but it was a real surprise when compared to all these other machine learning methods, this very old idea of having a neural network started to prove itself to be the state-of-the-art method. Really surprising when AlexNet came out, or similar things in NLP from Benjio's lab and so on. And they started really achieving state-of-the-art techniques. And so the thing that I want to point out now is that we actually have another real genuine earthquake that's happening again that we're living through now. You know, we've gotten all so used to the tricks that we can play with these deep networks, but there's something genuinely happening with the type of new types of learning that seem to be emerging in GPT-3. I think that it's genuinely something new again. And so we get these new phenomena that happen. And the weird thing is that almost all the way back to the 1960s, 70s, certainly the 80s, we've been doing the same thing. These are fundamentally the same type of architectures, the same type of routine. It's the same story. We keep on doing the same thing. We're basically optimizing these neural networks, learning parameters, fitting them to a problem where we're trying to match some data. You know, we've gotten a little bit more clever with the architecture. We've gotten a little bit more clever with the objectives over the years, but fundamentally we're doing the same thing. What has changed is we just keep on making our systems bigger by a lot. You know, each one of these pictures here is another 1,000-fold increase in scale. And in the last few years, well, I guess we've decided that we've caught on to this game that scale is good. I guess the last leap is 3,000. You know, we seem to be going even faster. But every time we increase the scale, even though we don't really have anything different that we're explicitly teaching these models, in language modeling, we're still up to the old game that was, I think you can find this probably back in 1983 or so, of just making a neural network predict the next word, right? We're still predicting the next word, but somehow from this very simple task of predicting the next word, we're getting these unbelievable capabilities. How many people have been playing with ChatGPT over the last few days, right? And it's quite entertaining, right? And so I'm a new professor. I worry a lot about how to assign homeworks and what to put on my midterm. And so I thought, well, I've got to test, you know, how good my midterm questions are. So I thought, well, let's see if ChatGPT, without taking my class, can answer some of my tricky questions. So I took a question that my students are having trouble with a little bit on the midterm. This was not the easiest question on the midterm. I showed the students a piece of code. I said, does the following code implement a classifier and autoencoder? So students, after taking the class, they should be able to look at this code and say, you know, I know, okay, I don't want to put you on the spot, but can you tell if this is a classifier or an autoencoder? That's a machine learning, deep learning question, right? What does it look more like? Who thinks this looks more like a classifier? Okay, you don't have to raise your hand, because I don't want to count points off of anybody. But I'll tell you what GPT chose as the answer here. So let me I'll put the code up here, the relevant part of the code. And so here's my midterm question, and you can see it defines a neural network architecture in PyTorch, and then it does something with it. And then this is what GPT-3 says, or ChatGPT says. So so somebody pointed out to me, oh, it has a 50-50 chance of getting this right. It's quite easy, right? And it's just like, yeah, but it guesses it right. It says it's an autocoder. But it impressed me because it didn't just do that. At first, then it went and defined what an autoencoder is. It's a reasonable definition. And then it went through a walkthrough of the code and stepped through, it sort of translated this code into English. It says, first it does this, then it does that. First, it passes through a bottleneck layer with this number of units, reduces the number of features from 1 million to 100. Then it goes to another layer that attempts to reconstruct the original. And then after it does that, then finally there's a loop here which computes the reconstruction error, and then it prints it out. This is a really great summary of what the code is. It's incredible. And it gets all the numbers right. So I thought, wow, that's amazing. Now, this is not the problem that all my students had trouble with. Here's the thing that none of them got right. I said, okay, when you actually run this code, it always errors out. Has a bug in it, and it has one of these terrible bugs where it always runs out of memory. And so you run this code, and it always results in an out of memory error. So I asked GPT exactly the same question I asked the students, So what's wrong? Can you fix it? And here's what GPT says. It says, okay, the issue is you're doing too many things at once. Maybe if you separate it into batches, then you won't run out of memory, blah, 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 right? Has all these things. So actually, this is very plausible sounding. Like if you had a surface reading of the code, you think, oh, this is the bug. This is what GPT says here in words is not actually the cause of the memory leak in this situation. To actually understand the memory leak, you have to, it's a curious thing about PyTorch, right? Where PyTorch is always building these computation graphs unless you turn them off. And the reason it's leaking memory is because we're just doing inference here and we forgot to turn off, the construction of the computation graph. So it's preparing to do backprop and using up all the memory while doing it. So that's the thing I was hoping the students would notice. And some of the students recognize this and other students didn't. It's a challenging question. And GPT here it misses it. It says, oh, maybe divide it into smaller batches. The thing would run out of memory anyway, even if you divide it into batches, except that if you look through the code, so it copied the code from my original, except it added this little loop to correctly batch it into little batches instead of whatever I did. But then it didn't copy it over exactly. It added this little thing. And what does this do? This detaches the result from the computation graph. It actually fixes the bug. So this answer is correct. And it's not, the words are not correct, but the code is fine. And so I thought, oh my gosh, what is going on here, right? This model, it knows how to do this. So I thought, okay, there's something going on here. And so for me, this is a pretty nice example of, wow, these models have these capabilities, but when you ask them to sort of explain themselves, they might not even understand their own capabilities that well. And so yeah, let me give you a couple other examples. So here's an easy example. The ChatGPT and GPT in general has like a lot of knowledge. If I ask it some question about anything, who makes a Philips Hue light bulb? Well, you would think it's Philips makes it, right? But that's not true. It's Signify is the name of the company, and it knows that, and it gives me all sorts of information. GPT knows a lot of facts about the world. How do I get to Adnet from the Andes Capital Gate Hotel? This is a question I had when. Who knows who's staying in the Capital Gate Hotel? Who took an Uber to get here? Right? It's just right here. It's attached. So the problem with this is that ChatGPT is so fluent, so authoritative sounding. You think, wow, this is really, it knows what it's talking about, right? Look at all this advice it's giving me. Depending on traffic, it might be longer than 15 minutes, right? Yeah, and you might require a transfer. It sounds very authoritative, but it's actually pretty bad advice. Probably the Uber guy would be happy to take my credit card, but then I'd be surprised to show up a block away. Okay, so and then the other thing that you notice in ChatGPT, and I'm sure you've all run into this, can you tell me who has recently been elected? We had these presidential elections in the U.S., congressional elections in the U.S. just a week ago, and they're very interesting. But as soon as you ask a question like this, instead of telling me that it's Josh Shapiro, we hit these guardrails, and so it's sort of both interesting from a systems point of view and also disappointing as a user. They've put up so many guardrails around ChatGPT. Every time you start asking it something that you think, oh, this is going to be an interesting one, then you get one of these results. So I'm sorry, OpenAI told me I'm not allowed to answer this question, and so there are ways of tricking GPT into trying to answer questions like this. But if you ask it in a naive way, it'll warn you that it doesn't know anything about new stuff, and is one of the open areas and one of the open problems. So, but because these models are so good at explaining themselves and their own limitations, it leads to this question. Maybe if we just fix these bugs in these models, maybe if we use a little bit more reinforcement learning to try to give them more demonstrations to GPT, how to explain itself to us. Maybe English is enough, right? Maybe our mission of model interpretability is now done. Maybe our job is done here. Maybe English is enough for model interpretation. So I'd love to have a sense for you. Who feels like maybe this is okay? Like, and who feels like, no, this is not okay. Most people think it's not okay. Yeah. And so this is my, obviously is my feeling as well, that English is not enough. Because these models are genuinely doing things that we don't understand as they get more capabilities. We're running into this. So let me pull back to computer vision a little bit. In the vision world, we've been playing with these image synthesis models a lot. So this is DALL-E 2 pictures that it can make when it came out. And here in vision, we're also facing this question of, is English going to be enough? Because this task of generating images from free text used to be considered a really intractable problem, but now it feels like it's very close to solved with these big models. And so if you can sort of name everything, then maybe you can write down in English anything, any visual concept that you're interested in, and be able to read it directly out of an image synthesis model to understand what it can do. And so, the remarkable thing about it is that it's sort of the quality of the images that you get out. And so even though the model has learned how to make these novel compositions of like putting objects in rooms, so I can like put a lamp in a room, the thing that is kind of amazing about it is that it doesn't just like paste this object in here. You can see that it's really solved the rendering problem, right? You can see that there's this really difficult light transport problem, which is sort of an obsession from the graphics community. And if you put a lamp in the room, you can see this nice, the nice reflections of the light going onto the wall and to other objects and shadows and these amazing things. And so when this came out, the first thing I did with DALL-E is I said, okay, well, let's take a look at this. How do you control this? I want to tell the model, turn the light on. It's happy to do that. You can use text to control this thing. Bedroom with a lit lamp makes all the lights lit. And let's do the opposite. Let's have a bedroom with an unlit lamp. Let's use some text to control this, and I'll show you what DALL-E makes. Yeah, so they're all wrong. The vocabulary with an unlit lamp seems to be missing from its capabilities. And it's not just like I chose this word unlit, that's not a good word. Like I tried a whole bunch of different words here. So here's all the synonyms I could think of. Here's a bedroom with a darkened lamp. I guess the bedroom is darkened, but the lamp is still on, right? How a dark lamp. How about, if I'm really explicit, how about a lamp that is turned off? A bedroom with a lamp that is turned off, right? Right. How can we turn the lights off, right? So what's going on here is that DALL-E is trained on this amazing data set. And actually, if you look at Stable Diffusion and the other models, they're trained on very similar data sets, which is these caption data sets, which is just any free-form text that somebody used to describe a photograph. Leon 5B collects together 5 billion of these captioned examples. But if you think of what you would use to caption an image of a room that happens to have a lamp, you might mention the lamp, but if the lamp was turned off, you probably wouldn't say, this is a turned off lamp in the caption, right? If it was lit, you might say that, oh, this is a very bright lamp. But if it was turned off, it's just something that you just wouldn't say. And so every model that I've tested that's trained on captions has the same problem. And it's a shame because this is like this amazing capability, but the English doesn't really give us the ability to test and understand what's going on here. So, we've got this extensive data curation we've done, but then after days or weeks or months of training, we get this model that bakes in all of these biases that we don't necessarily have a good handle on, and it's difficult to deal with it, because this is just, if you think about it, this is our programming interface for machine learning models today, and it's not the most convenient programming interface, right? It's very unwieldy. So what's the goal? I feel like one way of thinking about the goal of what we're trying to do in this room is trying to, create an interface that looks more like this, right? That once you've created one of these models, can we, put the human engineer, maybe even the human user, more directly in touch with what the model is doing without a giant opaque piece of data and weeks of training sitting in between. And so my slice of this that I'm going to talk about today is direct model editing. And I think that I'm really optimistic about this view of interpretability in the way that it can lead to some insights. So let me give you an example, a really simple example of direct model editing, and then I'll talk a little bit about the Rome paper, which is what brought me here today. So in the vision setting, we've had this phenomenon with sort of lamps in rooms for a long time. GANs have been around for a long time, so we've studied them pretty well. Diffusion models are newer, so we haven't studied them as much. Let me pull out an example from one of my students, Audrey, who was looking at lamps in GANs. And she was taking this approach of, generating lots of images and then asking, what is the role of a specific neuron in the GAN when you generate an image like this? So, for example, is there a neuron that's responsible for throwing the light on the wall out of that lamp? And so here's how she devised a really nice intervention way of answering this question. So first, generate a single image that has the phenomenon that you're interested in, just one image, right? And then in that image, find the parts of the output that you're interested in asking this question. Like, so what she was interested in is, there's these great reflections of light on the wall here. And so she wants to ask the question, what computation in the model is causing this effect to happen? So she asked this causal question, this mechanistic causal question of, like, how does the model do this? So after you do that, you can go through the model components. And so it's very natural to ask this for every neuron in the model. This model has maybe 30 million parameters, but actually a much smaller number of neurons, several thousand neurons that you can look at as candidates for this. And so the query is, can we identify neurons that are decisive in causing this effect that Audrey was interested in? So from a single image, she started with this. And then what you can do is you can go through and test each neuron by zeroing it out and then continuing the computation and regenerating the same image. So we literally remove the neuron from the network. And if you notice, with that neuron removed, the image looks a little different from the original. And you can do this mechanically and just create a difference image. And then once you see the difference image, you can create a score by intersecting the difference image with your query mask, right? So here's the query mask down below. And that'll just give you a number of, like, how many pixels, how much pixel difference, how much reconstruction loss falls in this mask that you created there. Okay, so that gives us a score for what happens if we removed one neuron from the network. And now every neuron has a score. We just loop over the several thousand neurons. It just takes half a second, and we can get a score for every neuron in the network. Now, so it gives us a search engine way of retrieving neurons. And so here's like the ranking of all the neurons, and it's a visualization of the difference map you saw on this image. And so the top ranking neuron was at layer 8. We don't have a good name for this neuron, but it's neuron 265 and so on. And you can kind of see what the patterns were. And so this neuron, it turns out, corresponds to task lighting. It's actually a neuron that seems to control lighting. And then but you get other neurons here that are interesting too. This one seems to affect the size of a light in the scene. One is actually sort of how reflective walls are, and not about like, well, how much light is coming out of the lamp. And this one was really interesting. So we were actually collaborating with the Philips Hue people that I mentioned earlier from Signify, and they're very much into the color of lamps, like the warmth of the light and so on. And so we found, oh, there's this channel that corresponds to the color of the light as well, and the network can do that. And indeed, if you the amazing thing about it is that once you've done that retrieval, just using a single image to find out what causal effect these neurons have, you can test them. You can test their generalization on other images. So if you just find other images that have lamps in them, and you take these neurons and you flip them on and off in those other images, you can see that indeed these images can turn lights on and off. So the remarkable thing about this is that even in a setting where it might be difficult to find training data with English words that describe whether a light is turned on and off, we just don't have labeled data for that. Just solving this very difficult task of modeling the data distribution of images, the model has found that the efficient way to solve this is to abstract the idea of whether a lamp is lit or not into its own neuron. And if we can identify that component of the model, then we can actually, reconstruct this abstract concept, even when there's no English that corresponds to it. So I think this is, I think that there's something deep about this example. It's a really clear example of this happening. Not all phenomena in these models are so disentangled, but I thought this was a very nice illustrative example that I wanted to share here. And so let's see here. This is, I think what I'm showing here on the right is the color changing neuron. So you can see that the lamp being a little bit more bluish and a little bit more yellowish. And so I was surprised by this, right? The Philips people have been asking me about this for a long time. And I thought there's no way we're going to, sort of find this, but the model already figured out that we should have color temperature as one of the separate variables. Okay. So, so what have we done here? So the general method is we're interested in some specific kind of change, and some specific mechanism or some phenomenon in the model. We're going to look for the mechanism by searching for causal effects, causal computations that are decisive for that. And then after we find some candidate causal things, then we find a way of double checking it. Because what's really interesting to us is if this causality that we find in a single instance actually generalizes, if it actually is how the model works in other cases. So not all these might generalize in the way we'd expect. So we have to go and we have to test on other cases to see what the model's actually doing with this stuff. So I feel like there's two steps here, looking for causal computations and altering the network. Okay, so those are the principles here. So we've got this two steps. Causal tracing, right, is like a really effective way of revealing mechanisms inside a model. And then to verify your understanding, what you want is you want to make sure that you have an ability to make intentional changes, that based on your understanding, you think that you can change something in the model. It's like important to verify that you can do that. And so, okay. So the main thing I wanted to show you. So how many people here are familiar with the Rome paper already? Okay, so a fraction, maybe a third of you. So I'll go over this paper a bit. This is more relevant to our conference here today because it's in the natural language setting. But what I'm going to do is I'm going to take the same idea that I showed you in Vision, and I'll show you how to apply it on a large language model. Now, the thing about large language models is that, like I showed you in the first slide, they've really gotten quite large. Even a small GPT model that I can fit onto, a big GPU here, is still orders of magnitude larger than the GANs that I was showing you that playing with here. So we actually have to introduce some extra cleverness to deal with the size and complexities of these models. And so, despite the size, I mean, these models are still trained in a very naive statistical way. We're just, predicting the next word based on, some gigabytes of web text. But after we train these models, they have these amazing capabilities. They know things about the real world, which I think was surprising a couple years ago when BERT came out, and it seemed to have a lot of real world knowledge. I think we've all gotten used to this, but I still think it's this amazing emergence here. If you ask GPT to complete a sentence like Miles Davis plays the something, it'll know, he plays the trumpet. It'll give you the correct answer. And if you changed the musician to somebody else, then it would predict the right instrument for a whole variety of different famous musicians. GPT knows who plays what. So the question is, how does GPT know this? So I'm asking a little bit of a different salience question than we would normally do here. I think that it's pretty clear that GPT must know this because we mentioned Miles Davis. And so if I figured out how to do salience maps over the input, I wouldn't be surprised to find out that Miles Davis was like the important decisive input. But I'm asking a salience question over the model. I want to know what parameters in the model are responsible for storing the knowledge that Miles Davis plays the trumpet. And let me show you how we can construct a causal query to do this. So, yeah, I guess the challenge in GPT is that the information doesn't flow in a straight line through the model. We've got this big grid. It's a big graph with multiple paths from input to the output. And so in concept, what I'm asking is there a sparse path through the model, which is the decisive path? Is there a subset of the computations, which is the decisive computation? And so the idea is to answer this, we're going to actually transplant data around. We're going to do an intervention where we force neurons on and off. We're going to force them into certain states to identify the effects. And so here's how we're going to do it. So we're going to run this network twice. First, we run it normally. We can get the network to predict Miles Davis plays a trumpet. But then we're going to run it a second time here where we prevent the model from actually solving the task properly. So think of this one on the bottom as sort of the baseline case. We'll say blah, 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 blah plays the blank. And it's like a truck rolls by or the fire alarm goes off when somebody says Miles Davis, and the model can't quite hear it. So physically what we're doing is we're actually inserting noise into the embedding of the key information of the subject of this sentence. And then when we inject noise, it prevents the model from making a good prediction here and knowing that makes sense, right? So think of this as sort of the disease condition, right? So now we have a damaged model that can no longer solve the task. And now we're going to go look for a treatment that can cure it. And I know that I can cure it if I told it Miles Davis. That's fine. But I want to know if there's a mediator that can cure it more economically than that. Because I know that in between Miles Davis and trumpet, there's many thousands of neurons. So is there some set of neurons that if I were to cure those neurons, it would actually cure the whole problem? And so what I'm going to do is I'll maintain this corruption at the front, but I'm going to monitor the output in the back. And meanwhile, I'll take a single hidden state from the clean model and use it as medicine to try to treat the damaged model by copying the hidden state over into the damaged setting. And then usually if you do this, it does not cure the patient. right? So here's an example. I'll just copy this hidden state over, and I run the model, and it propagates the effects of this hidden vector over, and it doesn't really do anything. It doesn't help the model predict trumpet. But I can repeat this for every state. And then once in a while, when I do it, then information will flow through and actually yield the correct answer in the end, right? Does that make sense? Any questions about this funny little process that we're doing? So we literally, just like in the lamp case that I show you, once we have a nice intervention that we can use to try to create the effect that we want, we can just iterate this over all of the thousands of hidden states in this computation graph, and then we get these neat little heat maps like this. So I'll show you in white. I've changed the sentence here to have more words so that we have a little bit more geometry in the heat map. And but in white we have all these states, which if you try to transplant the clean run into the model, it doesn't really have any effect. But if you, but the surprising thing is that there are a few states that if you copy them over, it does cause the model to recover the knowledge, the ability to echo the knowledge that it had. And so, so in B, on the lower right here, you've got these states which are actually kind of unsurprising. These are the very last few states right before the model makes its prediction of the word. I guess Brian De Palma works in the area. He's a filmmaker, so he works in the area of film. Yes, question. Yes. Yeah. So if you switch off, yes. Oh, let me repeat the question. So the question was, in the GAN setting, we had a simpler thing where we just turned things off and observed how they work. And why can't we just, why do we need to do this double run? And why can't we just turn things off to see which ones are effective? So in concept, you could, but what we found is when you set like hidden states to 0 in the GPT setting, the model is a little oversensitive to that. So if you think about it, I guess a machine learning way of saying it is that turning this hidden state vector to 0 pushes the model way out of domain. It doesn't function well at all like that, and it'd be the equivalent of just like poisoning the patient. And so if you do that, then you find out that and so I guess what you would be looking for is you start with a healthy patient, and then you add this little poison in different places and see which pieces of poison, remove its ability to say trumpet. And then if you do interventions like this, then you get these very diffuse, heat maps, which sort of say, oh, poison in all these different places causes all sorts of damage. And it doesn't really give you a clear picture at all. And so we had to fashion a more gentle sort of intervention than that. That's why. Yeah.
Yes. Oh. As a follow-up, how did you design the noising function on the input tokens such that it didn't likewise poison everything?
Yes, it's a good question. And it's like a good reviewer number 2 question, right? Because so actually there's a couple ways of doing it. And actually the first way that we envisioned this was to keep it in domain. One thing that you can do is, instead of introducing noise here, you could actually have a different word. I could put a different name of a person in there instead of Miles Davis. And I could say, oh, my baseline condition is Bill Gates or something like that. And it has no idea what instrument Bill Gates plays, and then I'll copy it over from that state. And so that keeps it really in domain. I guess what it leads to is it leads to this dilemma. What's so special about Bill Gates? Maybe we should do something else. And so I guess one approach that you could take to try to keep it completely in domain is make a large sample of different different subjects and average over that sample. We found I thought it was just easier to explain just adding Gaussian noise. And so the amount of Gaussian noise we add is is matched to the variance that we see in the embedding space when sampled over a large set of tokens. And so actually, interestingly, my hope was that we could get a good level of noise by matching the variance equally by setting the noise that we add to like equal to the amount of variance that we see. It turns out that's not enough. When you add only a small amount of variance, or that turns out to be a too small amount of variance to get these effects. And we actually use 3 times. Where's the number 3 come from? We use 3 times the amount of variance that we see. And so one hypothesis is that the embeddings are very non-isotropic. They don't have variance that's the same in all directions. And by multiplying by the number 3, we're sort of doing a better job at capturing the high variance directions, which are the important ones that are carrying the information for this. And we have to sort of noise them out for this method to work. If we actually use multivariate covariance, then we can actually match it exactly and get nice maps out like this. But that's sort of a slow computation to compute. And so in practice, we just use 3 times the spherical variance. Does that sort of answer your question? Okay, sort of, close enough. Okay, reviewer 2. But I think it's a reasonable question, and there's different approaches that you could use to establish this baseline condition. I'm not religious about we should use Gaussian noise. There may be other regimes that are more principled. So once you do this and you establish your baseline and you ask the question, are there hidden states that can recover the computation? You get these very unsurprising states at the very end, where we're right before the model is about to utter the word. If you put in the clean hidden state, then obviously it's going to utter the word, because what's encoded in that hidden state is the hidden state is effectively saying, please say the word film. And we put it there and it's going to say the word film. So this lower right business was not surprising at all. But then we got this upper left business here, like these states really, really early in the computation, where if we did that also, it would also say film. And to me, this was kind of a shock when we saw this. We thought, oh, we'll just set this experiment up. Who knows what we'll see? Maybe we'll get some diffuse heat map over the whole state. But instead we saw these pretty concentrated things, which is very, very interesting. So the early state at A is surprising. I'll show you that it generalizes if you try it on different types of sentences. It seems to show up in the same place pretty consistently at the last token of the subject on sort of mid layers from between layers 10 and 20. You see this concentration of effect. This is an experiment where we're taking Shaquille O'Neal, who would normally play the sport of basketball, and we're using Megan Rapinoe as the noise or something instead of using Gaussian noise. And you can see that, if you substitute Megan Rapinoe's state, it flips over to soccer. So you can use these other things. And so as a shorthand, the hypothesis that this sort of led us to was that, there's this word choice that the model is doing, but one of the important components of word choice is knowing who your subject is, knowing who Shaquille O'Neal is. Shaquille O'Neal is a basketball player. And if we can intercept this knowing phase so that that Shaquille O'Neal is a soccer player, maybe that's what's going on at the early phase, right? This knowing concept. And so so let me show you this other experiment that we did. I guess this is representative of real day. I guess I picked this randomly. It's not the cleanest example, but you can do this patching thing on just the attention outputs or just the MLP outputs. And if you do that, then you consistently get this other interesting pattern here, which is you still get these two locations, but what happens is on the MLP side, the contributions are very, very strong on the early state and not very strong at the late site. And attention is the opposite, where attention has a really strong causal mediating effect at the late site and not early. So this is pretty interesting. It's interesting, and it's also this neat opportunity. This idea that you've got to have some attention mechanism here that sort of copies information down to the last token is consistent with this way that that Catherine Olson and the folks at Anthropic have been thinking about attention heads. It also suggests that there's really interesting thing that's mediated by just the MLP layers, which were not as well studied. And so we thought, well, let's take a look at that. Let's see what's going on there. So attention moves the information down. This is just a piece of data that shows that I've been showing you a lot of anecdotes here. So this is averaged over 1,000 facts. And this shows that the phenomenon is systematic over a large sample. And so you can see that both early and late sites emerge, and then the MLP is really important at the early site, and the attention is really important at the late site. And you can also see that there's a few cases where it's being processed a little bit differently. I can talk about that. Okay. So far we've done this causal tracing, and it's revealed this really interesting mechanism of this early state sort of retrieval, or at least this invocation of the MLP layers to do something that has to do with understanding, what you're doing. So, and it's led us to this hypothesis that, maybe factual recall is being mediated by the MLP layers at this early site. But we have to do the second half here, which is, okay, we think we understand what's going on. Let's double check now that we can actually have this gives us an ability to make changes. So I'm going to briefly show you what we do to make changes. And if you have more questions about it, I'm happy to answer them either here in the talk or offline. But the basic mechanism that we use for making changes is to view a neural network layer classically, like people would have looked at it in the 1970s. Just you've got a layer full of neurons, and it's just a matrix, right? It's just a linear operation that maps some inputs to some outputs. And if you have any matrix, it can store memories. If you have a question, then you can program a matrix to remember an answer by just making the matrix solve this system of linear equations. So if I have like a whole bunch of questions, a whole bunch of answers that I want, I just solve the linear system of equations, and that matrix will be able to recall all these question-answer pairs. Let's see if I have a slide for this. I think I've skipped the slide for it. You can generalize this a little bit past. This limits the number of questions and answers you can have in a matrix to the number of rows that matrix has. But you can pack more capacity in it if you're willing to accept some error. And the classical way of looking at that is the least squares problem. So if you have a whole bunch of key value pairs that you want to store, but you want to store them and be able to retrieve them with minimum error, then you can find the matrix which solves this linear system with the minimum squared error, which is 10 minutes. Okay, so let me zap through this setting. It turns out that if you just use that abstraction to solve the linear algebra of what we'd want to do with a linear operation, if you patch it to change the key value mapping, then it turns out that there's a really small change that you make in the matrix to do that. It's a rank 1 update. So it's a rank 1 matrix edit or a rank 1 model edit, which leads to the acronym we use in the paper. We call it ROME, R-O-M-E. And the idea is if you have a key value pair, then if you solve some linear algebra, then it tells you exactly what you want to change in the matrix to insert that key value pair into its memory. And the neat thing is when you solve all the math, you can minimize error with all the previous memories that were previously memorized by this matrix without actually needing access to what those memories were. Like all the terms cancel out. and you can just do this local update. So that's pretty neat. So if you have a sentence like oh, the Eiffel Tower, Space Needle. Okay, well, if the Space Needle is located in Seattle and you want to have the Space Needle located in Rome instead, then all we have to do is find the key that corresponds to Space Needle and find the value that corresponds to Rome, and then insert it into this matrix. And so the way that we do it is to find the key, we just run the network and we collect how key is encoded at this layer, at this particular location. To get a nice robust key, we run this several times with different random prefixes, and we average them. That gives us sort of a nice average key. They're all very similar, but the method works a little bit better if you get a nice average. And then to get the value out, well, this is kind of a challenge. We don't know how Rome should be encoded at this point in the network, this attribute. So what we do in the current paper is we just set up the sentence and we do backpropagation to find out, what value should this vector take in order for this particular sentence to predict Rome instead of Seattle. So we do about 20 iterations of gradient descent to do this. Now, to be clear, when we're doing backprop, we're not affecting the parameters of the model. We're asking this question about the activation vector, the state of these neurons at this question. So like all the parameters of the model are frozen when we're doing this backpropagation. That's why we can do it so quickly. Okay, so we get this vector out, and then once we have a key in a vector, we do that linear algebra I talked about to insert it in the matrix. And so then when we input Space Needle, it output the vector for Rome, and then once you do that, then indeed the network will say Rome in the end, which is great. But it's actually not that surprising because there's a whole bunch of different fine-tuning things that you can do to get a network to say anything that you want in the end. The real question is, does it generalize? So like this would be the equivalent of me showing, like, I have the ability to turn on and off the lights in one room, but I want to ask, can I turn on and off the lights in all sorts of different rooms? So I'll show you the Space Needle in the city of Seattle example here. So normally it would say that Space Needle's in the city of Seattle, and if we get it to say Rome instead using our method, then if you form other different types of completions for GPT to answer, then you get these really interesting entailments out. So from the Space Needle, you can see the water stuff. I've tried to form a sentence where we're not using any of the same words, and it'll say, normally it would say like these sort of Seattle locations, but after you change it, then it says, oh, you should see like the Tiber River, right? And would give you the chance to brush up on your U.S. geography skills. But if you rewrite the model and you have it complete this, then it'll answer with something like this, pretty different. And the space burger, I guess when you're in the U.S. you should eat burgers, right? Is that what the model likes to say? But when you're in Italy, right? This is what it recommends. And I thought so these kind of entailments sort of fall out of the model. Let me so Kevin Meng, the first author on this paper, this great idea of how to quantify these kind of effects, and created this data set where we can actually measure generalization and specificity systematically. And I'm running a little bit short on time, so I'm gonna zoom through it. But the point that I want to make here is that there are these two effects, right? That you can, if you want to change a model, you could do it badly in two ways. You could either change the Space Needle so it's in Rome by changing everything in the world to be Rome. If you ask the model, where's Empire State Building? Maybe it would show up in Rome. Where was Bill Gates born? Maybe he was born in Rome. Where do the New York Giants play? Maybe they play in Rome. So that would be a lack of generalization. The other way that you could fail at doing this is a lack of specificity. So if I said the Space Needle is located in the city of Rome, if I had one way of doing this wrong would result in a model where I said, the Space Needle is in downtown, and then maybe it would go back to Seattle again because I've chosen like a different phrasing, different way of saying it. So that would be a lack of specificity. So we have this benchmark that can measure both generalization and specificity. And the interesting thing is that, if you take different methods to try to see how effective they are, and you graph sort of generalization versus specificity, you see this really clear trade-off that in different instances, they really succeed at specificity, but really fail at generalization, or vice versa. And you get this sort of Pareto frontier of what the models are able to do. So in purple, you can see what like hypernetwork, the state-of-the-art hypernetwork method can do when changing this kind of fact in a model. In red, you see what the best fine-tuning method can do. And then in green, you can see that when you use Rome, when you use this interpretable method where we identify which layer to do the intervention, we do it directly. You still get this trade-off, but it's up and to the right. So the method works quite a bit better. Okay, so there's quantitative numbers. I read the paper. It mostly tells the same story here. Now, this whole paper in Rome was done with one fact at a time, and so people started asking us, well, I have more than one bug in my model that I want to fix. What happens when you do a few facts at a time? And it turns out you can just repeat Rome a few times, and you can fix about a dozen things before the model starts having trouble. But then after you repeat it maybe a dozen times, the model starts to degrade. But we have this new result that's on arXiv called MEMIT, where we take Rome and we rework some of the math, thinking through what would you want to do properly if you had multiple facts that you want to change all at once. MEMIT will spread the change over multiple layers instead of doing the change all at one layer, and then also balances this error minimizing thing by solving the least squares problem in a slightly nicer way, where instead of just inserting a single vector and a single key at once, each of these keys and vectors, can actually be like a whole matrix of keys and values at the same time. And so when you work this out, you get just slightly different results, but they result in a model that, so this here is like how well Rome scales if you just repeat it. These are the hypernetwork methods. This is how well Rome scales if you repeat it. And this is a log scale here. So you can see that as you get to about 100-fold changes, Rome starts to degrade pretty seriously. It does okay if you're at about a dozen. But with MEMIT, with adjusting the math and understanding what's going on in a little bit more detail, we can actually scale all the way up to about 10,000 before we get bad degradation with this. So I thought this was pretty interesting, because there's this thing which I'd say is a common fallacy in our business, right? Which is, we traditionally think that there's some trade-off between interpretability and performance. Like the more interpretable the method, our intuition is, the worse performance we're going to get. And I like to point at the examples that I've shown you here as potential counterexamples, where actually, in principle, I feel like if you really understand what's going on in these models, if you have better interpretability and a better understanding, in principle, it should lead to better performance. And I feel like this is a good goal for us to set in front of ourselves. Let's as a community, let's strive for this, for the kind of understanding that leads to better performance in the end. I think that this is the kind of thing that'll lead to sort of a virtuous cycle of more transparency in models, more capabilities, more understanding of what's going on. So okay, yes, bulk updates. We had these guardrails where GPT chat was unhappy, telling us who was elected in 2022 because it wasn't trained on it. So my students were excited when the election happened to insert them into the model, and you can see that we've done this. So let me see here. I'm gonna wrap up here. So before I wrap up, I just want to say, all the hard work in the project was done by my students. On the lighting project, it was Audrey Kui, along with Ali Agata Rohit Shaheen, and my advisor Antonio at MIT, and then the brilliant student Kevin Mang, along with his other terrific collaborators, did the Rome work, and so if you ever have a chance, you should meet them. It's a great team, and so thank you very much.